right. Hello, everybody. Welcome to PDH Hour with Glenn. I'm your host, Glenn Tepfer. This is uh, December. I'm going to be talking about mastering extrusion weld examination, essential checks before, during, and after welding. And I thank you for joining. I apologize I didn't have anything in November. Schedule's just been crazy. So hoping I can keep at this next year on a regular basis. As a reminder, prior webinars can be found on the CQA Solutions website, but we can only award PDH hours to those of you who attend the whole live session because that's the only way we can verify who's been on. So kind of an outline here as we get going. I'm going to do an introduction, really mostly assuming that everybody here is pretty familiar with extrusion welding. I'll get into an overview of the importance of the topic, why we're spending an hour on it today. It probably should be more. Some of that will talk about the welding parameters because those are keys that you look through throughout the whole process. We'll get into the before welding. And as I was putting the outline together, I realized we really need to back up and start with the design and then the technical specifications before we actually get into the field inspection. Then your during welding inspection, I broke up into two categories, trial welds and production seaming and repairs. And they're all going to build on each other. Really, what I mentioned in before is going to be things you look through in the during and trial welds and things that are mentioned there, you'll look through in production seaming. But then we get into different things to look for in the after welding inspection. I'll talk about a comparison between the before, during, and after, give you a few tips at the end, give you a brief overview of the next webinar, and then we should have time for questions and answers. Yeah, remember to use the question and answer feature on your browser if you have any questions, and I'll get to those at the end of the session. All right, as we get started here, I think the introduction I wrote for this was about the Titanic, and really, as we go through this, you'll see why I compare it to the Titanic in more ways than one. But April 15th, 1912, was the day that the Titanic famously sank after hitting an iceberg late on the 14th of April. Approximately 1,500 lives were lost. Accounts state that the Titanic was ordered to proceed at full speed ahead, even despite multiple iceberg warnings. And the research I did, there were at least 6 reported warnings on the 14th, iceberg warnings. They say that the vessel was traveling at 22 knots. And because of that speed, when lookouts seen the iceberg, they couldn't avoid hitting it. They couldn't turn fast enough because of that speed. And I think, that's one of the things in our industry, particularly in relation to extrusion welds. I think a lot of times it's full speed ahead, and I think we need to actually take a little warning and slow down things. And I'll show you why here as we get into it. Really, one of the things is, trifecta of trouble, as we coined it last night when I was finalizing the PowerPoint here. But extrusion welds really are error prone. They're difficult to weld, and their locations typically aren't, the best places, or they're being extrusion welded because you can't run a wedge welder there typically. So part of the error comes from, it's human dependent, more human than the wedge weld, which is, thought to be much superior weld to the extrusion weld. In this photo, you have you're going through the process. You have 3 or 4 main processes before you even get to the welding. You have to heat tack, and before you heat tack, if you need to bevel the material, you need to bevel the material. Then you need to abrade it and grind it. And finally, you have to have somebody put the weld on, the final weld. So it's a multi-step process with human involvement across the entire way, and as such, there's room for human error. And then we'll get into the locations. Here's an example. There should be caulk on the top of the batten strip, hopefully, but you can see on this vertical wall, there's a horizontal extrusion weld taking place on this structure. And that's, where they have to hold the machine, support the machine in the air, which makes it more difficult than when you're welding on the ground. You're fighting gravity when you're supporting the machine. Similarly, here's welding on a vertical structure where they're doing a vertical weld, but they're also, going around. So they're doing some horizontal, different angles, and they have to keep that uniform pressure on there if you want a uniform weld. And I'll get that into that in a little bit here. Um, Location, intersections. You're always going to have your repairs at intersections. Tie-ins, a lot of tie-ins can't be um, wedge welded for one reason or another. And you look at the whole scheme of things, and this is an as-built of a cell that I used in a previous presentation, but all of these dots here are intersections. Each one of those is going to have an extrusion repair performed on it. And some of these tie-in up on the north side here was extrusion welded. Some of the area in your sump down here was extrusion welded. Just a lot of different things going on with the welding as far as it all adding up. A lot of people don't realize how quickly the extrusion footage adds up, but we looked at a bunch of our projects and really came up with, an average, a 10-acre project averaged between 3,000 and 5,000 lineal foot of repair seam. That doesn't include your regular production seams. That might have been a tie-in seam. This is all just repairs. So you're putting out nearly a mile of extrudate on a 10-acre impoundment or containment system, and or whatever the project may be. It could be a cap, whatever it is. But these are all, labor intensive inferior welds, and for the most part, the quality is really not being monitored that much on it. And that's, part of the reason for this webinar really is to look at that and give you all some things to think about. As I mentioned, extrusion failure rates are typically higher. This is from a paper I did back in 2015, and haven't had time to really look at new numbers. But you see failure rates 9%, 10%. Sometimes, some cases we had 0%. Most of the time, though, your extrusion failure rate is going to be higher than your wedge weld. It's going to, your wedge weld, people say you can be at 1%. I don't think that number is really realistic, at least what we see. It's, probably 2 to 3%, is target. 5% definitely can be met with a wedge weld, but with a good crew. But your extrusion welds, if you're at 5%, that'd be phenomenal. You're probably going to be closer to 10% at a minimum. And you have a bad crew, it could go south a lot quicker. So that really brings us, from the Titanic to today, December 18th. Where are we? And as I was thinking about it, I thought, well, our purpose of our containment systems is to protect aquifers. So the Titanic, they lost 1,500 people approximately. How many would be impacted by contaminated aquifers? If you look at the Floridian Basin in the southeast United States, I forget exactly how many states that impacts, but it's an area of 161,000 square kilometers, and that supports nearly 10 million people living across the region. Similarly, the Great Artesian Basin Aquifer in Australia, 1.7 million square kilometers, but that only supports 180,000 people across the region. But size doesn't really matter. You don't want to impact it, regardless. You want to keep the water safe and clean. I'm going to butcher this name, I'm sure. I was trying to say it last night, but the Ogallala Aquifer in the Great Plains region of the United States, approximately 450,000 kilometers squared, and it supports about 2.3 million people living across the region. So we want to, protect those people. Um, and extrusion welding is a pivotal and important part of protecting our groundwater because it's an important part and a significant quantity of it in our containment systems. And just like the iceberg with the Titanic, you're looking at a finished um, extrusion weld here. This is a coupon we had for sampling. Everything looks good on the surface, like the Titanic. Maybe they thought the iceberg was smaller. I haven't read it in detail there, but um, like they say, you don't know what lies below the tip of the iceberg. And when you look at this, you can see here's the center line of the weld. That joint should have been, over here where the blue line is at. That's where your physical joint is at, but it's not there. And you can see some squeeze out on the one side here. It's a little bigger than the other side, and I'll get into squeeze out in a bit. But those are things to look at for the quality of the weld too. It should be uniform if your person doing the welding has uniform pressure on, which we'll get into. Um, so you just can't see what's below there. Excuse me. Then it ties into your heat, speed, and pressure. As I mentioned, I think earlier, those are the three things you really want to look at as we go through this whole presentation, as well as location and the other things I mentioned there. But to get a good weld, you got to do your best to make sure you can get that heat, speed, and pressure. And Eddie Weiser from Leicester had presented this magic triangle concept years ago to me. And you have your heat, speed, and pressure for any different material, and within that, you're going to find, your HDLL. You're going to find a sweet spot for your material where your welding is going to be the best quality. But, even before that triangle, you need to have a good foundation in conjunction with it. There has to be clean and dry geomembrane. In the case of the extrusion welding, all the preparation steps have to be properly performed as well. And how do you look at heat, speed, and pressure with an extrusion? You have two different heats on the extrusion gun. You have the heat that melts the resin in the barrel that is forced out and becomes the actual extrusion bead itself. And you have the preheat that heats the surface ahead of the extrudate. And both of those are important, and you want to keep them uniform throughout the process. Speed is manually controlled by the operator. And pressure, what a lot of people don't realize is, there's two forces required. You have the force of the extrusion welder against the geomembrane, and a lot of specs call out that you want adequate force against the geomembrane, but you got to have that substrate below there for resistance. If you have a wrinkle, the extruder can push down. You're not getting a good bond in the wrinkle. You're not getting that resistance pressure you need, and that's something that a lot of people overlook, unfortunately. So I'll try and get through the design here. Some of the things about design. One of the biggest issues is constructability. You can see in this design here, this pipe is flush on the ground. There's no way to do a good boot. There's no way to get a good weld on that. So these things need to be considered when you're talking about the design. And this photo here really shows you the insufficient clearance around the pipe to get welding equipment. Even whatever he's doing up here on the top, if he's going to try and do that underneath, I've seen people just fit it in by hand and try and roll it with a roller because they can't get the extruder in there. But we need to design things better. We're setting ourselves up for failure for poor weld quality because you're not getting the pressure, in some cases the heat. Design constructability. Here's an extrusion weld that was performed between all these rebar pieces, which, that's hard to fit anything in there to even get that done. And then they only use silicone around the penetrations to seal them. You can see here in this other picture, the other photo, the guys working in a confined area. He's putting wire in for a holiday spark test, but that's a hard area to weld there. How do you get uniform pressure with the extrusion gun? Those are all things that really need to be taken into account with when you're thinking about any type of welding, but especially extrusion. Lack of incorporation of some of the things that are available in the industry. There are corner pieces, prefabricated corner pieces made out there. In this case, they fabricated it themselves. They actually got the weld out away from the corner, But there's going to be no good way to seal this corner there. It's going to be a potential leak, and it's right at the bottom of the containment unit, right where you don't want something that's going to be problematic. Here's an example of an actual prefab corner that was used on a project. This project had both prefabbed inside corners and outside corners, and so this is one of those that was used, and it helps um, get the weld out and away from the corner itself. And a little better quality, you still have to make a transition at the bend, but it minimizes those as well. So I'll get into the technical specifications here. Let's see. All right. Yeah, thought I was having a glitch here. We had a computer glitch earlier trying to get set up. Um, so technical specifications, a lot of times they mention the welding rod, and here you can see there's a SCAPS high density and a polyflex high density in the photos, and they say it's supposed to be the same resin as the geomembrane. But what does the same resin mean? You know, everybody that you talk to will say that it means it has to be, if it's linear low, it has to be linear low welding rod. If it's HD, it has to be HD. But what about the same manufacturer? And nobody will really answer that question, And so based on what I know of it, I think it should match the manufacturer. Really, ideally, it would match the same batch as the geomembrane being made because there's proprietary variances between manufacturers. And even though the material may meet the GRI GM 13 and 17 requirements, for LL and 13 for HD, there's variances in there, the proprietary variances, and how are they going to intertwine with each other, their chemical compatibility, melting points, things like that. So I think it's, something to consider, and it really should be the manufacturer itself. Heat tax, these are another thing that often is left out of the specifications is that, excuse me, when these heat tacks are done, a lot of people think they're watertight. They're not watertight. They'll minimize the flow of water, but they're not impermeable, and water will seep under them. Frost will get under them. Even moisture from your soil will creep out from under them. So they need to be removed if they're sitting through a moisture event or they're left overnight. They need to be removed and replaced. And any heat degraded material, they need to make sure it's a larger patch. But that's typically left out of the specifications, and you end up with poor welds as a result. Trial welds, one of the things we recommend are doing vertical trial welds. Hang the piece of material there and make them do welds in the same conditions if it's vertical or horizontal. In the case of a batten strip or these horizontal welds, make them do that because the pressure is entirely different there. You're fighting gravity the entire time instead of allowing gravity to work for you. And we've felt that, doing this has helped us at least increase the quality or, at least having a check on the quality that they can actually do a trial weld. Expertise. A lot of people, all the specifications say, oh, you have to have a master seamer with X amount of footage overseeing everybody. But it's not just a welding operator. Look at this guy here. He's grinding. You should never see a grinder like that. If you see a grinder like that, he's just gouging the liner. He's cutting it. He's not grinding it. Somebody like that, I'd kick him off the job site if I ever seen that, but they don't let me, but I want to. But I try and get them removed from the uh, doing that activity because they just shouldn't be doing that. Similarly, every step of the way, you have your heat tack person, they might be doing the beveling. The whole welding team should be qualified and they should keep doing only the positions that they were qualified on as part of the trial weld. You have your guy doing the grinding, your person doing the welding, obviously, but that's not the way the industry typically works. But that's, I think the way to get the best quality. And a lot of that stems from my experience at Palo Verde when we did the zero leak project, between 2009 and 2012. There was a time where a guy kept failing and kept failing. Well, there were two guys that kept failing on it. They had success, but then all of a sudden they were failing. And one guy gave up. He was a great wedge welder. He had welded good and he got failures and couldn't get rid of them. And he just gave up. But the other guy a different guy came on and ground for him and did the grinding, and that guy told me, he's like, he's not going to fail because I'm grinding for him. And he was right. I mean, he didn't fail anymore in the project. So the grinder makes a big difference, and that's things that we need to keep in mind. You don't want to see people going in and out of the different positions. It should be the same person the entire day. But that's not what we see. But I think that's the best practice. Understanding the construction practices and purposes. We do a lot of constructability reviews and we see, technical specifications. This is just another one of my industry pet peeves, but excuse me, but I've seen it a lot lately in the specifications is, abrasion is to be performed to clean the geomembrane. That's not the purpose of abrasion. That's the further thing from the purpose of the abrasion. If you're abrading it to clean it and you're going through dirt, that dirt's just going to get trapped on the grit and transfer it into your weld, and you're going to have a bad weld. So that's something that should not be in the specifications. The grinding is really to assist the bond and really remove the oxidation on the polyethylene materials for a good bond. We should require wrinkle removal or dispersion, and you don't see this in the specifications, but I mentioned to you, you don't have that resistance pressure when they're going over a wrinkle. And on this project, I took a bunch of destructs on these type of things, and probably 95% of them failed because they just don't have it. Same here on the right. You can see, the weld's starting to sink in there. They don't have the pressure. Maybe they lost their overlap there. It's hard to tell. It looks like there's separation, but you don't have that pressure, and that really should be required. A lot of times these wrinkles can be walked out. If they can't be walked out, then they should be cut out and repaired. Another thing missing from the specifications and really causes a lot of the issues in the field, I feel, is that there's just no acceptable guidance on the weld configuration. And there's a future ASTM coming out on that, and I'll be happy when that comes out because I think it will help alleviate some of this, at least, excuse me, as we move forward. But your weld thickness should really only be 1 3/4 to 2 times the sheet thickness based on a lot of information, a lot of research by people. Your squeeze out should be limited. It should be uniform on the sides. Your grind should be covered, and it shouldn't be too wide. It shouldn't be too deep. And as we go here, I'll illustrate, courtesy of Eddie Weiser with Leicester, some images that he has. And the red area is your extrusion weld. You see the bevel there. You have your width of your welder. The area underneath the weld should be ground, and then your thickness should be 1 3/4 to 2 times the height of the geomembrane. And your weld configuration, you can see here, Eddie's diagram has the squeeze out, and you can see that studies have shown that with excess squeeze out, you get more heat there, you get crack propagation vulnerability, and that can cause stress cracking in the future. So you want them to be uniform, but the recommendation is that they should be 1/8 inch in height or less. So now I'll move into before, as you get into the field, I'm kind of through the design and technical specs, and so we'll get into more of the things to look for in the field here. One of the things I mentioned earlier, I think, but the shoe configuration and quality. You can see the extrude comes out of the shoe. It's formed by the shape of the shoe. You can see different shapes for different applications from Demtech's website here with one of their extruders. And you want to make sure that you have the right shoe for the right application. It needs to produce a weld that's going to give you that 1 3/4 to 2 times sheet thickness. So that means that if you're working on 40 mil and you go to 60 mil, it's possible you need to change your tip. But a lot of installers will grind these out and make their own shapes, and those shapes don't always conform to what the general guidance is. And especially in the winter, cold weather, the practice used to be, they'd grind them out pretty deep and you'd have a real thick weld. And, everybody thought that's better, but it's been shown that the weld doesn't cool uniformly and you end up with crystallization and cracking in the long term with those welds because of the quick cooling, the flash cooling, and the colder temperatures. Power supply, this is another big one. And while you're out in the field and things are getting set up, there's recommendations that the manufacturers have, and these recommendations should be followed. The Pro-X from Demtech suggests a generator that has minimum output of 5,000 watts. However, they prefer a rating with 6,500 watts or more for better performance of the welder and better temperature control. Um, and that's one of the things, we were on a project, one of our technicians was on a project this year, and they were doing trial welds with generators that met these requirements. And then they'd unplug them and they'd go with those small portable generators. I don't even know what their output is, if it's even 1,000 watts, but they'd go use those and do their production welding. And we told them they shouldn't be doing that. And the engineer approved it for a while, and the owner wanted it done too, and we did 40 mil, and things were passing with a wedge and the extrusion, and when it got to 60 mil, things were sporadically passing now, so they ended up using the big generators that met the requirements the entire time. But it shouldn't come to that. It should just be done correctly the first time. It shouldn't be that people are allowed to cut corners like this. And the same thing goes with your extension cords. How many of you have ever looked at the extension cords, measured the length, see are they within the requirements or not? The manufacturers have certain requirements. They always recommend minimizing the number of connections, and they have maximum lengths that they say you should go, excuse me, as well as the gauge. So there are limitations there, and those are things that you should be looking for every day when you're in the field. Other items, you'll see in the manufacturer's operations manuals, um, proper warm-up of the extruder. Usually there's a recommended warm-up time, and a lot of times you're seeing people aren't doing that. They get out there, fire up the generator, and then, they start welding right away. Proper preparation. So with the extrusion weld, you got to have, all those other factors, your trimming, your overlapping, and then your beveling, heat tacking, your grinding. So all of that can be looked at, and you should be looking at it ahead of time. And then make sure you have a firm substrate before the welding even begins, because you can get things fixed before they weld rather than after. It's a lot easier to deal with. It's easier to deal with if you get it done before they start cutting the liner too, if you can catch it quick enough. So moving on to what do you want to look for, during the welding? I'll start with the trial weld section here. And again, all of these things carry forward. I'm not mentioning everything a second or third time because they all kind of build on each other. Proper substrate. This is usually written into the specifications, and it's, so-so on whether it's being followed. Some sites we see a good job on it, others that we audit, we find, aren't even coming close. But here you can see the guys welding an extrusion trial weld on top of a piece of GeoNet, because that was a configuration of the project. I think it was primary on top of a secondary GeoNet, or a primary, whichever it was called, a GeoNet on top of the secondary. So they're replicating that. You can see he's grinding here. He's probably grinding a different interface there, a textured smooth or something like that, so that they can test the other interface. But this guy doing the grinding, he should actually be the one doing the grinding then for the duration of the welding performed that day, or for the trial weld for which he was tested. And the importance here is shown in this photo. You can see this was actually cut out of a patch we took a destruct on because there was a sunken area, but they were overheating the tees, and in this case, the extrudate was overheated so much it forced itself through the underlying geonet and bonded with the geonet when it cooled. So, it shouldn't be doing that. You shouldn't even be getting that overheat, but that would have had, disastrous consequences with the expansion, contraction of the materials, as well as any stress that would have come on it during use. Another common one that we see is the purging. The purging, this is an extrudate ball. In the extruder, every time they stop it, there's going to be a certain portion of um, extrudate resin in there that's been heat degraded that hasn't come out of the nozzle. And so they need to get that out of there. So they usually purge it. And you want to make sure that they're purging it long enough to remove anything that's been degraded, as well as you don't want to see them throwing it on the geomembrane either. They need to properly dispose of it. But you also want to make sure that the welding rod or the pellets going into the extrusion gun are always clean and dry. Um, so then trial welds, as you go on, you get your coupon inspection, and really you should be inspecting that whole length of the trial weld for everything we're going to discuss here. That's part of it. You don't just look at the coupons, you look at the trial weld as a whole, make sure they're centered, things like that I'll get into, but I'll start with the coupons. And you can see, they're going to be tested. You want to make sure that the installer's not cherry picking the best spots. And you should look at it, if you got a place you want them to test, then they should test it there. Then you're going to examine for peel, for shear, and then you're going to examine for, obviously for more things. Um, Peel, obviously your peel separation. Here's 100% peel. It's not always cut and dry. This one's a partial peel. You can see some of the white there. Is it greater than 25%, which is, most often the cutoff? I don't know, but our recommendation is always to start the trial welds with 0% peel incursion allowable. Why let them start with anything more that's, closer to the maximum? If they're starting at the maximum, there's no room for error. If they're starting at the minimum, then they have a little bit of flexibility. Maybe, there's a speck of dust. Maybe there's something else that's, not going to cause it to fail. Shear, shear, this is the table from GRI GM19A. And one of the things that I disagree with on the GRI is, note 2 here, elongation measurements should be omitted for field testing. And I disagree with that, particularly for extrusion welding, because I've seen them fail. If they grind too deep, if they, overheat it sometimes, usually it's the grind, as far as I can tell. Um, Usually the grind causes them to have elongation that's less than the 50% required. And if you're not doing that out in the field, I understand why they don't want to do it. They want to speed the process up. But, again, sometimes full speed ahead isn't the best course. And I think this is one of those, at least for extrusion coupons, because we get destructs back that fail. We get a few back every year that fail elongation. They're 25, 30% elongation, they fail. And now you got to track destructs. Now you got a bigger problem. You got to fix things when potentially you could have avoided it in the first place with your trial welds, which is the whole purpose of the trial weld to begin with. I just threw in the locus of break. You should be looking at the locus of break just to make sure they are passing and that you're familiar with these when you're examining the coupons. Then you want to look into other things that indicate weld quality. Is there a bevel? If you have contrasting extrudate, it's a lot easier to tell if there's bevel. The white extrudate on the black is pretty nice for that purpose, but you have black on black. A lot of times you're not going to be able to see it, so you have to physically be there to make sure that they're beveling. And that's just an unfortunate truth, but you can see no bevel here, was pretty obvious. Is the weld centered? We discussed that one earlier, but here's another example where that one, you'd be lucky if it even holds together just passing it around in our classroom most of the time because it's so far off center, it's unbelievable. But again, you can't see that when you're looking at a finished weld from the top. So you see any of these things that are issues, you should be failing the trial weld. You should make them do it, right. If they got areas, that aren't adhering, if they're over grinding, they have dirt, anything in the weld. This is an example where there's moisture was getting in a weld. Sometimes you'll see it not as much in the trial welds, but we have had where people are dripping sweat and drip into the weld, and we got to ask them to put a headband on or do something like that to help reduce the sweat. But again, grinding, you see any of these things on a trial weld, it shouldn't just be based on peel and shear. Should be failing them, you know. Um, again, squeeze out uniformity. If they're having problem with doing the squeeze out, this isn't a trial weld, but they're doing, round the bend here. Um, they weren't getting uniform squeeze out. Their weld profile looks a bit off on this for whatever the shoe would have been. Your heat penetration, this is signs that there's separation. The material's separating there, so you're not going to have any strength there. So it's going to be an issue. Same thing here. It's overheating. They're sucking the base material up from the heat. It's bending drastically, almost a 90-degree bend. That's going to pass a peel test because you can't make it peel when it's bent like that. I mean, your material is going to fail because it's bent so bad, but that's bad for the long-term liner. It's going to be crystallized. It's going to be, overheated, become brittle, and be a weak point in the system. Then your lack of heat penetration as well. You can see this in a trial seam. Here's your weld, but in here where the seam is, there's no heat transfer. So you should see a minimal indentation on most of your sheet products that are showing that you have at least adequate heat penetration. Some of the other common issues, I mentioned too thick or too thin of a weld. We've seen welds that are paper thin, and of course they fail, but they shouldn't have even brought them to test when they're that thin most of the time because those will typically fail. Too thick won't fail, but I mentioned the inconsistent cooling. The excessive heat, the burn through, so one of our practices we suggest is a T-bead during the trial weld. You can't physically test that with your peel or shear, but you have them just weld up into the weld that they were doing for their trial weld, and you look at the bottom and see if there's enough heat penetration there. If they're overheating it, it gives you a better feel for whether their T practice is going to be successful or compromise the liner while they're actually doing it in the field. Especially because a lot of projects won't let you take destructs on smaller repairs. But if I take a destruct on a patch, I like to have the whole patch cut out because I don't want to crisscross welds, which I'll get into later, but that allows you to look at the T's as well. But the big point with the trial welds is if they're not going to do it correctly on the trial welds, what makes you think they're going to do it correctly anywhere else on the project? And that's why the whole team should be tested. They should be tested as a team. So moving on to the production seaming and your production repairs. Again, you need your clean, dry materials. Your top sheet has to be beveled, uniform heat tack, clean and dry, all the basic things that we've basically discussed. Proper width of the grind, and your time of the grind. You need to make sure that it's covered within the allotted time because otherwise dust gets in there, it oxidizes. Again, once it oxidizes, it's not going to adhere. And again, just my pet peeve, so many specs I've seen lately, abrasion is not being performed to clean the geomembrane. We just need to learn that. If you have that in the spec, it's just going to compromise the weld. So why do we need the grind? As I mentioned, it helps the extrudate adhere. And you can see here a couple of examples where the area was not ground. I was on a project, I don't know, 2013, somewhere back in there. And it was a shale gas project. And we called them chuck in a truck. These people, mom and pop things just showing up overnight. They got equipment, and I'm asking, the foreman what he's going to weld, and if he's going to extrusion or fusion. I don't know. It's a Demtech. I got the best equipment in the world. It's a Demtech. He didn't have a clue, and they didn't know that they needed a grind on the HDPE for the extrusion. So at the toe of the containment slope, when I inspected it, all of his beads were laying at the toe because they fell off the wall that he had welded them to. And these welds, these extrusion beads, even if you have a pinhole and you're using it to cover a pinhole, which I never recommend. I think pinholes should be patched, but I've seen it personally where they ran an extrusion bead over a pinhole. They dropped a air test needle or something, and I happened to see them do it, and they did that, and they're like, "Oh, it'll be okay, it'll pass," and they vacuum boxed it and they spark tested it, as it was a conductive material. Both passed, but it would fail in the long run, so I made them cut it out and repair it. But these things will lie to you and give you a false sense of security. But again, you're not going to know that it wasn't ground if you weren't there when they put it down, unless the bead's laying there like it was on the project I was on. But grind inspection, this one, again, this was another shale gas project, but these people shouldn't have even been allowed to set foot on the project. But you can see the grind is pathetic here. They don't have it consistent. You need consistent grinding. But if they somehow manage to cover, this, you wouldn't know that only one side is ground and the other one isn't once it's covered. You got to be there to inspect it. Um, grinding through dirt, paint, things like that. This is one that I use in some of our training. Um, you can see I don't have the photo where it was finished welded here, I guess, but they abraded through the paint, so they got the paint all over the place and scattered with the grinding disc, and then they welded through it. Under full-time CQA, we were doing an audit. Well, here's your two CQA people. They're down at the toe of the slope. They're not paying any attention to what's going on there. You need to be up and seeing things firsthand so you can catch these problems and deal with the problems. I mentioned, is it being placed in the proper time frame? Here you can see that the welding operator looks like he's, trying to keep a good pressure, nearly vertical there, actually tipping it back a little bit, maybe so he can see. And the grinder is right ahead of him, but eventually you want to be careful that you're not too close because that grinder will throw dirt and debris back into the area that you're welding, and the preheat may not blow it out. So you want to be careful that you don't get too close in that. But it should be covered within the allotted time frame, and you really need to pay attention at the end of the day, at the end of shifts, as well as lunch breaks. I've seen a lot of things that were abraded before lunch, and they're supposed to be covered in 30 minutes or an hour. Crew goes away, comes back, it's an hour and a half till they get started, and then they weld it. Well, that was outside the spec. It needs to be repaired, and it needs to be repaired with a larger patch because you can't weld over that grind at this point. Improper weld angles, you need your heat and your pressure. So you have a vertical extrusion on the photo on the left here. You can see this guy's got it tipped back so far back, I don't know, it looks like 20, 30 degrees to me, maybe more, but you're not getting uniform heat. You're not getting uniform pressure. It almost looks like he doesn't even have it, square. It might be leaned a little bit to his right or something. So you got to pay attention to these things in the field and stop the installer and talk to him when there are these issues. Don't allow him to continue doing poor practices. Um, so what do we look for after? I talked a lot about what you look for during. What are some of the things, you're out there and you're going to walk on the geomembrane, so you're seeing the extrusion. What are things that you can identify? It's not as much as it would be if you were out there while they were doing the job. If you come out there afterward, you're not going to catch as much. But multiple passes. They should never do multiple passes. And here you can see what looks like a sunken extrusion weld. So if you see something sunken like that, it's a good idea to take a look at it, maybe cut it out, have them redo it. Avoiding overlapping welds. Every time you overlap, you're reheating the liner. In this case, it looks like they might have welded over a wrinkle as well. They should remove the wrinkle. It should be laying flat there. They got like a fish mouth started there. This whole conglomerate should be cut out and made one repair so that you don't have all this overheating. And that's what, if I take Destructs on repairs, I try to take them on smaller pairs and maybe something this size and take it on both sides or something so I can get my sample and they can put a patch over it because I don't want them to, overlap and make this type of a mess because it's not good. This one is on our website. You can look at our website if you follow this link here, but it's an interactive patch on our website. This one, came out of the shale gas. I've been passing it around for over 10 years now, probably, but it had just about everything wrong that could be wrong on a repair. I think they might have had one or two things right, and maybe they had a couple inches of stuff right there somewhere, but pretty much everything you can imagine was wrong. Those people shouldn't have even been out there attempting to do this, but they were, and that's what we run into in the industry. So we just gotta stop it. You see bad stuff, get it fixed. Improper termination is another one. This one, these people frustrate me too. Another pet peeve. I'm tired. I'm going off on people. I just like to kick them off the job site if I could, but um, they yeah, it's just laziness. They should terminate. They should run the bead out flush, let the extrudate stop, but they pull it up and they leave these protrusions all over the geomembrane, and they shouldn't do that. We talked about the cooling differential and thick weld. Same thing happens here. You can induce stress because of the different cooling rates, as well as, what if you're putting another material down on top of it? Now you've got all these sharp protrusions all over the place that have to be dealt with, and they can be ground down, but what is grinding them down due to the extrudate? I'm not sure. That's something I don't know, but I don't like it, and that's something that, they shouldn't do. It just indicates laziness. Visual inspection here. You can see where they welded over wrinkled material, loose material. There was no substrate there. Their welds look pretty bad. What we had to do is, have them cut this section out, have them pull the liner taut, and make a better weld. But you see things like this, if it's not in the specifications, people are reluctant to deal with it. It takes twisting the engineer's arm sometimes to get things done, and it shouldn't be that way. Excuse me. And I mentioned sunken areas here. You have the sunken area, the separation, these you can find out in the field a lot of times when you're walking around after the welding's done. Improper repairs where, there's a wrinkle here. They should have continued the cut. There was a cut made here. They sealed it with the extrudate, and that's going to be a bad joint. It's going to fail at some point because you put stress on there. It's going to pop off of there. So they should have continued it, and we had to make them, do the proper repair later. So as I mentioned in the beginning, the introduction, I was going to do a comparison here as we, start to come to a close of this webinar. And from the field inspection perspective, before welding, during welding, the trial and production welding, and then after welding, can you confirm these items? Can you guarantee that they followed the specifications? Were they done properly? And the Ys indicate, you can see them, the welding rod, was it approved? Yeah, you can check what they're using all the way through the production welding. Once it's down on the ground, unless you won't know what was welded. It could have been HD, it could have been polypropylene or something, you won't know. Power supply, you can catch the whole time. Proper equipment warm up, you can catch. Substrate or absence of, you can catch it all the way up through after welding. One of the pictures, couple pictures I showed you, you could see that it wasn't excuse me, didn't have the proper substrate below it. You could tell that by the weld quality. The preparation activities, your beveling, overlap, heat tack, were the heat tacks that were left overnight removed? Did they undergo any moisture? You're not going to know. You won't know anything afterward. You have to be there to see it to know. And, with the moisture, I've seen where operators, a couple projects I've been on where the operator's welding and there's moisture either coming from the subgrade below or frost, something like that. And the operator really doesn't see it because they're bent over the gun and they don't see right ahead of the gun. But if you're inspecting and you're standing there, you can see a little water bead being pushed sometimes, and they're welding over it, and it's not even showing up as bubbles in the weld because it's so small. but it ruins the weld. We took a destruct on it and he cut it and there were voids there. And the installer was surprised, and he believed me finally, but um, it happens, and that the only way he wasn't trying to take shortcuts. He was trying to do a good job. He couldn't see it from his perspective. So, that's the importance too of third party inspection. When you get into the welding, most of these items, again, you can't see after welding. You get into your heat penetration during production welding. If it's a lack of heat penetration, you can see it, or you can't see it. If it's overheating, sometimes you can see it. Your speed, you're not going to know afterwards. Pressure, you have two different squeeze outs. You can see the guy doing things, we've seen him, dancing like Yogi Bear with their feet up in the air and behind their back like Michael Jordan and stuff, but shouldn't be that way. But, what does it mean? Nobody really defines what it means if you see that they're doing these things, unless you take a destruct and it fails. Is it off center? We already discussed that. Dirt and moisture. Sometimes you can see them afterwards, sometimes you can't. And as I illustrated, sometimes you can't even see them in the production welding, like the operator that I just mentioned. Exposed grind and proper termination, you can. So some of the tips, design um, with the extrusion limitations and concerns in mind. The things that we mentioned here, constructability, making sure that they have proper substrate, firm substrate, minimizing extrusion welds, I think is the way to go. Only do them if you have to do them. That's what we did at Palo Verde. You couldn't have an extrusion weld longer than 10 feet at Palo Verde with a zero leaks. And the repairs, if a destruct failed, that was going to be a minimum of 20 feet. Those were all fusion welded, and then we patched the ends, so we minimized the extrusion because the extrusion is problematic. Excuse me, but it's a necessary evil. So, with a necessary evil, the best thing to do is minimize it. Use the technical specifications to empower the construction teams. There's a lot of tips I gave you, like the vertical trial welds and best practices like that you can use and get them in there, the resin, things like that. Remember, inspection must be continuous and ongoing throughout the construction, and in particular for the extrusion welding. And, my recommendation, it's never been, except maybe since the early 90s when I started, but you should have one person inspecting each repair crew so you can keep track of what's going on. That's the only way you're going to see it. You can only keep an eye on so much out there. And if you're not right there with the extrusion, there's so many things that can go wrong. And you can see through all the examples I've given you, you're not going to catch them after the weld is done. And don't rely on visual inspections after the welding is complete, basically. As you can see from the tables, they won't tell you nearly as much. Excuse me. So with that, that wraps up this portion of the webinar. My next webinar really is going to be like last year, or this year really, I did a review of 2024. Next year in January, I'm going to do one on 2025, the year in review, findings from the field, earthwork and geosynthetics. I haven't yet begun to put that together, so I'm hoping that we're going to see some improvement from where we were at last year, but it's pretty much on a project by project basis, unfortunately, because you see some things that are improving, and then you have other crews like the ones with the generators that I was telling you about that just blow your mind and you wouldn't think they'd be doing it. So anyway, I look forward to presenting that January 15th, 2026 at 12:30 Eastern. And I will now take any questions and try and give you any answers. I'll see if I can get to the feature here. Stop share, I think. And Q&A. Hey, there's a Q&A. Quasi is asking me if I suggest that we specify the qualifications of the entire welding crew. That's an interesting question. I've pondered that in my mind, and I don't know how you qualify them particularly. I think probably similarly to the welding requirements, you could do that. You could say that they should have been performing this task for, X amount of projects, X amount of time, the grinding, the heat tacking, beveling, things like that. The extrusion welder, similarly, I think that they should. And then the actual true qualification of the team would be, the trial weld that it passes peel and shear, but we got to be careful there that they're not overheating too and cheating the system that way. But um, yes, that would be my answer basically is, yeah, I think we need to have something there that they're tested, and we could put something in there that the people are, doing that because we've seen laborers, that were out there picking rocks, and the next day they're helping do grinding or they're heat tacking, and they have no clue what they're doing. They could be burning holes under the geomembrane while they're heat tacking, and you don't know because you can't see it. They haven't been properly trained, so there should be some type of qualification on that, I believe. Let me see. I hope that answers you, Quasi. I appreciate your question. Um, Take another moment or two. I actually got through a webinar early. Wow. Um, yeah, if there's any other questions, I'll give you another 30 seconds here or so and see. I'm not seeing any other questions, so um, I know Clark Griswold was attending. I seen on the list, so I was kind of waiting to ask him if his newel post had been fixed. So, um, yeah, I appreciate everybody being here and look forward to seeing you next year. I hope you took something home valuable today and hope together we can change this industry and make the quality better. So, thank you for attending, and I'll see you next year.